Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, cousins in binary tree 2. The problem is fairly straightforward. If you haven't tried this yourself yet, I would strongly encourage you to try this yourself once. In this particular video, I would be showing you three different approaches to tackle these kind of problem in general, right? We will be going through all these approaches from scratch. So if you are complete beginner to this kind of problem, I am very sure this video would help you understand how to solve this problem in general. If you already solved the problem, you can actually go over different section of the video and at least see what is the follow-up problem that we are trying to solve, and try to solve that yourself first so that you gain all the understanding that I am trying to teach here. So with that, let's get started. The problem states that you are given the root of a binary tree and you have to replace the value of each node in the tree with sum of all its cousin values. Now, what is cousin? Cousin is all the nodes at the same depth with different parents, right? So you have to return the root of the modified tree, right? So let's say this is the tree, right? Now, cousin of 4, there is no cousin of 4 because cousin is defined as the node at the same level with different parents. So at level 2, there is only two nodes, 4 and 9, but 4 and 9 both have parent 5, which are same. So hence, there is no cousin of 4. Therefore, the sum of cousin values for this particular node 4 would be 0, right? Similarly, cousin value for 5 would be 0. Similarly, cousin value for 9 would be 0. Now for 1, you can see there is one cousin 7. Why? Because there are three nodes at level 3, 1, 10 and 7. 1 and 10 both have parent 4, which are equal. So 7 is the node which doesn't share the parent and and is at the same level. So therefore 7 is a cousin of 1 and 10 as well. So for 1 and 10 the value would be 7, right? Similarly for 7, 1 and 10 both are cousins. So for 7 the value would be 10 plus 1, 11, right? So hope the problem statement is clear. Now how to solve this? So we need to first figure out what is the sum at each level, right? Because what what we need to do is we need to just simply find, let's say we already have the sum at this level, let's say x, right? From x we can simply subtract the sum of immediate parent, right? That's what the definition of cousin is. Definition of cousin is all the node at the same level which doesn't share the same parent. So if you have this sum of all the nodes at that level, you can simply subtract the node or the children of immediate parents. So you can, for 3, you can, what you can do, you can simply go to 4, figure out the children of 4, which is 3 and 6, and subtract 9 from x, and you will get the value, uh, the desired value for this 3 and 6, right? So the first step therefore is to figure out what is the sum of each level, right? How to solve this? We can solve this very easily via DFS or BFS as well. If you want to apply BFS, you can do that as well. So what we can simply do is start a DFS with root node as depth or level as 0, right? And as and when we are going one level down, we will keep on incrementing this depth value. So let's say from 4 we transition to 1, we will say that depth of 1 would be 1, and similarly from 1, let's say we transition to 4, we will say depth of 4 is 2, and so on and so forth, right? So what we can simply do, we can simply maintain an array of size n, and we can go, we can start with root, right? Now every node we will just see what is the depth. So for this node the depth is 0, we can simply add the value to 0th index. Now we go left, let's say, right? And as we are going down, we will increment the depth as well. So now depth of this node is 1. So again we will go to the first index and add the current value. Now similarly we'll go again one level deep, the depth would be 2, right? The same way we will just add the current value to the index, and so on and so forth. So finally, once you do this for the entire array, you will be having the sum of each sum of the values for each of the depth, and your array would look something like this. So the depth, the sum of values at level 0 would be 4, right? Similarly, the sum of values at depth 1 or level 2 would be 4, level 3 or depth 3 would be 7, and so on and so forth, right? Now, how would the pseudocode look like? Pseudocode would look simply like this. What we are doing, we are simply doing a DFS. We start with a particular node root, right? And then we also maintain a depth variable. So initially, when we call this function, we will start with the root node and a depth value of 0, right? Now, as and when we are going down, we are incrementing this depth value as well. So what we are doing, we are simply first incrementing the sum at the current depth, and then we are visiting its left and right node, and while visiting left and right node we are also incrementing its depth, right? So after this recursion ends, we will have this array built out, right? Now once we have this array, what we can simply do, as we have decided, we will simply, let's say, maintain another empty structure of the tree, and what we will do, we will, for each node, we will visit its parent, figure out the sum of its children, and subtract from the depth. So for 4, the parent of 4 would be nothing, and the children of that. So for this node, the value would be 0, right? So for root node, everything, there is no other cousin at all for root node. So value would be 0. After that, for the children, what we will do, we will simply go to its parent, figure out the sum of its children. So parent of 1 is 4, sum of its children is 1 plus 3, 4. Now we will simply subtract 4 from the current depth value. So current depth was 1, the sum of all the nodes at depth 1 is 4, and we know immediate, the sum of all the immediate children's is also 4. So we'll subtract 4 from 4 and we will get 0 here, right? The same way, we will figure out the value for this, how this depth, sum of nodes at depth 3 is 7, right? And for 4 we'll go to immediate parent, which is 1. Now the children of 1 is 4 and 2, the sum would be 6. So we'll subtract 6 from 7 and we'll get 1. So this, the value for this node will be 1. And similarly, you can fill other nodes as well, and finally you can return the root of this particular tree, right? So hope this entire solution makes sense. Again, the main part was to calculate this sum at each level, and then we will simply go to the parent and figure out the sum of its children. So what is the time complexity? Time complexity would be, we are doing a DFS which would take order and time, and then we are doing one more DFS to actually fill up all the nodes of the answer, right? Or so there also we will take order and time. So time complexity would be order n. And what is the space complexity? Space complexity is also order n, because we are creating n new nodes. Like for each of these nodes, we are creating n new nodes, right? So space complexity would also be order n, right? Now, this problem we have solved by actually creating a copy of the original tree, right? So let's say you are not allowed to do this, like you are not allowed to make a new node at all, like you can't call new of tree node. So in the problem we have given this tree node class, right? Let's say the constructor of this class is private, and you can't actually call this new tree node at all. So in that case, you will not be able to build this tree entirely. So that's the first follow-up problem. That is, you have to solve this exact same problem in place. That is, you are not allowed to call new tree node at all, right? Now, if you haven't thought about this problem yet, I would encourage you to pause the video right away and try to solve this version of the problem by yourself, right? So again, hope you thought about it. The first thing is definitely will require the sum of node at each level, right? So sum of node, for sum of node. So okay, first let's look at here. We are doing two things. First, we are finding out the sum of node at each level, and after doing this, we are going, like for finding out the values at each node, we are going to its parent and then subtracting the immediate the sum of immediate children from this node, from this sum of all the nodes, right? So let's try to apply the same without actually creating a copy, right? So let's say we already have calculated the sum at each level, right, using the same DFS algorithm which we have discussed. And now let's say we are trying to apply the same thing. So for let's say 3, we are trying to find its value, and we will replace this 3 itself. Instead of creating a new structure and then updating that, let's say we update 3 itself. So what is the value at this particular node? The value would be 27 minus the sum of immediate children. So for 3, the parent would be 4, right? And the sum of immediate children of 4 would be 3 plus 6, 9. So we can simply replace this value 3 with 27 minus 9, which is at 18, right? Now, let's say you have to find the value at 6 now. So value at 6 would be again 27 minus sum of its immediate children, sum of the immediate children of its parent. Now parent of 6 would be 4, right? Now immediate children of 4 would be 18 and 6. The sum would be 24. And the value here would be 27 minus 24, which is 3. But this is wrong, right? Because the actual value was 3. 18 is something we actually overridden the value of 3 with, because we want to store, or we don't want to create a new node, right? That's why we have overridden the value of 3 with 18. And as soon as we have done that, we saw that while calculating the value for other nodes, the other nodes will not give the correct answer because the actual value was lost, right? So that's the problem, why you can't actually replace directly the existing values with the required sum of its cousin. So now how to solve this? So what is the problem? The problem is we can't simply replace this value. We have to first keep track of all the sum of its immediate parent. So let's say for we have, because so first of all we need to replace this value for sure. We have to replace this 3 with 18 and this 6 with corresponding value. But if we just replace it as it is, we saw that the answer is get not like answer is getting polluted for some other nodes. So that's where what we will do is we will simply try to pre-calculate and store the values which are required with the existing trees. So what is required? The required value is find me the sum of the immediate children of my parent. So for 3, the value required is 9, because the parent of 3 is 4 and sum of its immediate children is 3 plus 6, 9. So we will try to store 9 somehow. Now how to store this? Again, what you can simply do, when you are at 3, you can simply say, okay, my parent is 4. So parent of 4 is plus equals 3, right? You can simply do this. But this will also not work fully, because this 4 is not a identity for the parent. You can see there are two different 4s. Sorry, let's not take 4, let's say 3. So there are two different 3s, right? And when you say parent of 3 plus equals something, you lost the context that which 3 are you talking about. So basically each node doesn't have unique IDs here, and because of that you can't simply do parent of x plus equals something, right? So first you need to assign each of these nodes some unique ID. So how to assign a unique ID to each of these nodes? You can simply do DFS in a particular sequence. You can do DFS in order, pre-order, post-order. Basically, the motive is to convert this tree into an array, and whatever the position of a node was in that array, that would be its ID. So let's say the position of node 2 is 5th position in the array. So basically the ID for this node would be 5. And similarly, let's say the position of this node in the array is 7. So the ID for this node would be 7. So basically the motive is to convert this tree into an array, and because each each value in the array would have a particular index which is unique. Each of these node will get some unique indexes, right? So that's the motive. Now, to convert this tree into an array, there are different ways. You can do in-order traversal, you can do pre-order traversal, post-order traversal, any other way, right? So in this particular case, let's say what you are doing, you have a counter variable which is initialized to 0, let's say, or 1, let's say. And now what you're saying is, okay, uh, I will visit root and then left and then right. So I will first visit root and then left and then right, right? So this is the order I am going to traverse the tree. So once you have fixed this order, you have to traverse the tree always in this order, because otherwise the ID that was assigned before will be different from the ID that would have assigned if you traverse the tree in some other order, right? So let's say this is the order we are going ahead with. We will always visit root first, and then its left child, and then its right child. So let's start with 4. We'll visit 4. So ID of 4 will be 1, right? Now, as soon as we assign 4 as 1, we will increment this to 2, right? Now, we will go to left now because we have visit root, and now it's time to go to left. Now again, we will visit root first. So the ID for this is 3. We'll increment this to 3, right? Uh, Again, we'll visit its left child again because root is visited. Now we'll visit left. The ID for this would be 3. Then ID for this would be 4. And finally, this node doesn't have left and right child. So we'll go to this parent. And this node, we have visited left child before. So now it's time to visit the right child. So the ID for this node would be 5, right? And similarly, the ID for this node would be 6, 7, 8, 9, 10, and 11, right? So this is, we just perform a DFS and we got the ID for each of the nodes, a unique ID for each of these nodes. Now you can do the same thing. You can simply say, okay, I want to store the sum of of the immediate children of parents. So let's say you create an array where each index is the IDs. So one denotes this particular node, right? Similarly, this second index denotes this particular node, and so on and so forth. So now for one, like for this particular node, what you want the sum of the children of immediate parent. So the parent was 1 and you want the sum of these two nodes, which is 2 and 8. So what you can simply do, when you reach here, you will say, okay, I will add 1 to this node because this is my parent, and what I want, I would be just subtracting the value of the parent from the sum at the current level, right? So what I will do, I will simply add 4 to level 1, like to node 1. So we'll add 4 here. Similarly, when you reach 4, you will say, okay, I will add 4 to node 2, right? So you'll add 4 here. Similarly, when you reach here, you will say, okay, I will add 3 to node 3. So you will add 3 here. So basically, you will try to, what you are computing what is the sum of all the children of a particular node here. So for 3, the sum of all the children would be 4 and 5. So that's what you will be storing. You will be storing finally 9 here, right? You will be storing 3 plus 6, 9. So once you build this entire array, each node here would be storing what is the sum of all the children of this node, right? So finally, what you can simply do, once you build this array, you can simply come to any node. Let's say you have to find the value for this node. You can come to this node, figure out the sum at this level, this would be 27, and then subtract the value at node 3 because this value would contain the sum of all its children. So value at node 3 is 9. You will subtract 9 from 27 and you will get the answer 18 here, right? And similarly for this node again, you will subtract the sum of this level, which is 27, with the value at node 3, which is 9. So you will subtract the value at 27 minus 9, which is 18. So you will get 18 here, right? So hope this entire point makes sense. Now let's quickly look at the pseudocode. So what we are doing, we have to first assign IDs to each of these nodes and build this array where each node contains what is the sum of all its children, right? So for that, again, we can do simple DFS. As discussed, we will start with a counter variable one, right? And then start a DFS. Now, in this DFS, we will keep maintaining the parent index as well. So current index will be CNT++, right? As we have discussed, we are visiting the nodes in this order, right, left, sorry, root, left, and right. So this is, we have visited the current node root, and we also added its parent here, and finally we visited its left child and then right child, right? So after this entire recursion ends, you will have this array built where each node or each index here would denote what is the sum of that all the children of this particular node, right? Now after that, finding the value or of each of these nodes would be simple. You can again start with a DFS with same trick. uh, you will initialize CNT with 1, and now this time we will also maintain the depth as well, because you need to figure out what is the sum at particular depth, right? So you also maintain this depth. Whenever you reach a node, what you have to do, you have to simply calculate what is the sum at that particular depth and what is the sum of its parent, like what is the sum of children of its immediate parent, and you will subtract these two and you will get the value of current node, and you will just replace this directly here instead of creating a new node, right? So in this way, what we are doing, we are calculating the value of each node without actually creating new nodes itself, right? So again, if you don't understand this particular part, I would encourage you to rewind the video and watch this piece again. Here we particularly look at two different things. One, if the values in the array are not unique, then how to assign unique indexes to all the nodes. For that, what we have discussed, we can simply convert this tree into an array, and the index of that array would simply become the unique ID of that particular node, right? Now, converting the tree into an array, we can apply any algorithm. You can do in order traversal, peer order traversal, push order traversal, anything like that. In this case, what just need to be care, we just need to take care that whatever order we are applying first, we will apply the same order throughout. So you can see in DFS2, we have applied root, left, and right. So in this particular DFS as well, we have applied root, root, left, and right, right? So basically, if we apply the same order, every node will get exact same index, and that would be the ID of each of these nodes, right? So now the next follow up is, okay, so what is the time complexity? Time complexity is still order n. We are doing 3 DFS, that's it. And space complexity is order n plus d. Order n because number of node, you have a array where each node has a position in this array. So this array size would be n, and you have another array which is of size d, where d is the depth of the tree, right? So time complexity is order n, space complexity is order n plus d. Now let's say you have to reduce the space complexity from order n plus d to order d itself, right? So how to solve this? Again, encourage you to pause the video right away and try to think yourself first, right? So again, let's think about what was causing order n space here. So this array was causing order n space. And why we have to build this array? Because we can't simply replace the value here with the required value, because if we do this, the value of other nodes can be polluted, because it would take into consideration the new updated value instead of the older value, right? So that's something we need to tackle. Basically, we need to make sure that there is some way in which we are trying to apply the value. We are trying to replace the value here without actually interfering with the correct value of other nodes, right? So a simple trick here is, in the previous case, we were trying to fill the values in bottom up. We are doing DFS, right? And what we are doing, we were saying that we will go to the root part and then we will try to update the value of this and then that, right? So instead of doing this, let's try to fill the value from top down, right? We will first fill the value for this, and then we'll fill the value for all these nodes, then we'll fill the value for all these nodes, and so on and so forth, right? So this is very standard trick, and it is applied in very many different problems. One very smart application of this trick where we are filling the values from top to down is in out dp. I have explained that in a detail in one of the video. I would link that video somewhere in the description down below or in the top right I section. Make sure to check that out as well. So what we are saying that we will try to fill the values from top down. Basically, we will try to fill the values for this node first, and then this all the nodes at the next level, and then all the nodes in this level, and so on and so forth, right? So let's see how exactly that would help. So first of all, we actually need this anyways. So let's just copy it already and paste it. So we already have calculated the sum of each level, right? And this would take order d space, which is allowed. Now we have to fill the value for this node. So what is the value for root node? Value for root node will always be 0. So we'll just simply replace this with 0, right? Now, before going to this node and updating the value here, let's try to calculate the sum of all the children of this node itself. So what is the sum of all the children of this node? 1 plus 3, 4, right? Now, both the children will have exact same value after the fact as well. Basically, both are the children of the same parent, so they will have exact same number of cousins, and hence the sum of cousins for these two nodes would be exactly similar, right? And what would be that? That would be the sum at the next level minus the sum which we just calculated, which is 4, right? So the value for these two nodes would be 0. So we'll simply replace 0 in both the nodes. Now notice that the problem that we are facing previously will not occur now because we have updated the value for both the nodes. Previously, what we have done, we have updated the value for this node first, and then we go to the root, and then we come to right, and now we are trying to update the value for this node. So that's where we have updated the value for one node, which will interfere with the when we calculate the value for other node. But here what we are doing, we are updating both the children at once. So that problem will never arise, right? Now, once you updated these two, again we'll do the same same order of DFS. We will go to the left, let's say. Now we reach this node. Now at this node again, we'll do the same thing. We'll calculate the value for sum of all the children, which is 6 here, right? And then update the value for both the nodes at once. So what is the value? Value would be the depth, like sum of depth at one level down. So let's say the depth of this node was d. So sum of depth at d plus 1. So which would be 7 here, and the value for this would be 1, right? And finally again you will go to left and right, and in the same way you will calculate the values for all the node, right? So now you can see we are not taking any extra space for each of these nodes. Hence the time complexity is still order n, and space complexity reduced to order d from order n plus d, right? And what is the pseudocode? The pseudocode would look something like this. So what we are saying is we will update the value for both the children when we are at the root node itself, right? So let's say we are at the root, some node root, we'll calculate the sum of all its children, right? And now we will update the value for both left and right at this stage itself, right? So we'll update the value, and the value would be the sum of depth plus 1. Why plus 1? Because the children would be, the depth of current node is depth, so the depth of this children would be depth plus 1, right? So sum of depth plus 1 minus child sum. So once we update both the values, we will simply call DFS again on left and right, and that would fill in the values further down the tree, right? So hope this entire thing makes sense. uh, let's look at the actual code for uh, this particular algorithm, wherein we are trying to solve the problem in order d space. without actually creating new nodes at all. But I would strongly encourage you to code other two solutions yourself as well, because that would help you understand the problem in much more depth, right? So if you have, like, you can try coding both the parts by yourself. If you need any help, you can simply paste your code in your description down below, and I would be able to help you in case you are facing issues there. So again, let's quickly look at the code. The code is very similar. What we are doing, we are calling two DFS first to calculate the sum at each level, and then the final DFS to calculate to populate the node with the cousin sum. So what is the first DFS? As we have discussed, it is exactly similar. We just take care of one extra variable depth, and as and when we reach one particular node, we increment the value at that depth with the current value, right? And then we will update the value for, then we will call the same function for left and right nodes. And for cousin again, exact same thing we are doing. We are finding out the sum of child. These are some conditions for handling the null cases. Once we find out the child sum, we will calculate the value for left. Value for left would be the sum of depth plus 1 minus child sum. And we calculate the value for right and also call the same function for left and right. Right. And finally, we update the value for the root here, because uh, the root would always be have value 0, right? So we'll just we have to update this manually at the end, and finally we return root because we have just updated the value for this tree itself, right, without creating new tree. So hope this solution makes sense. If you have any doubts in any of the version of the problem, feel free to comment that in the comment down below, and I will be happy to help. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.